In this video, we'll go over the last answer key for this semester. That's Wednesday, April 29th. Here we're talking about inhibitors for enzymes. An inhibitor will reduce an enzyme's ability to speed up their reaction or reduce their activity. Inhibitors are different than inactivators. An inactivator completely shuts down an enzyme. It's irreversible. Now we have different types of inhibitors, and one common type is called the competitive inhibitor. And competitive inhibitors will compete with the substrate at the binding site. And they do this by resembling the substrate itself chemically. So here's a visual of that for the enzyme succinate dehydrogenase. It'll take succinate and make fumarate. Now if you take malonate, which is only different from one CH2 group, this will bind to succinate dehydrogenase, but there will be no reaction. So that is an example of a competitive inhibitor. You also have another one with Tamiflu, which it will go into your liver and react with an enzyme and make this compound, and ethanol. So Tamiflu is actually a competitive inhibitor for one of your liver enzymes as well. Another type of inhibition you can have is product inhibition, where your enzyme makes so much product, the product will bind to the active site and actually stop the reaction. And when we look at metabolism in Biochem 2, we're going to see a lot of this idea where one of your enzymes will make so much product, it will actually stop the whole glycolysis pathway from going forward. Now, when you are making inhibitors, one of the best type of inhibitor you can make is called a transition state analog. These will look like the transition state, but will be a little different. These are good because enzymes really want to bind to the transition state. So if you have something that looks like the transition state, your enzyme will want to bind it. So our first question is, so I have a substrate for enzyme X, that's in molecule A. Which one is more likely to be a competitive inhibitor, B or C? And the answer there is B, because it looks more like A than C does, where you take this carboxylic acid group and you just make it a CH3 group. Now let's actually look at the kinetics of competitive inhibition. And again, here's another example of competitive inhibition, where you have alcohol dehydrogenase. We'll take ethanol, make acetaldehyde. Well, methanol will actually work and create formaldehyde from it. So they look similar, but methanol is actually competing with ethanol for the active site, and it's not allowing alcohol dehydrogenase to do its normal reaction. It's slowing down the enzyme. Now, when we talk about inhibition, we have something called Ki, which is an inhibition constant. That's how we are measuring how good of an inhibitor we have. And Ki is called a dissociation constant. Basically, we're measuring how easy or how hard it is for your inhibitor to dissociate from the enzyme. So Ki equals the amount of free enzyme you have multiplied by the amount of free inhibitor you have divided by the inhibitor enzyme complex concentration, where a smaller number means stronger binding. Because if your number is smaller, that means the denominator is bigger, which means you have more complex than you do free inhibitor or free enzyme. Now for a competitive inhibitor, we use Michaelis-Menten to measure initial velocity, except now we have this term alpha Km. Alpha Km is called Km apparent. That is the Michaelis constant with the competitive inhibitor. And the Michaelis constant actually increases with competitive inhibition. our actual equation is alpha equals 1 plus free inhibitor divided by Ki. Now let's think about why it increases. Well, that's because your enzyme and your substrate are competing for the same site. Now, if you have enough substrate, you can completely outcompete your inhibitor. So eventually, you can get to your maximum velocity, and your turnover number are ultimately unchanged if you add enough substrate. However, since you are competing for that site, you do need to add more substrate to get to 1/2 your maximum speed. And remember, Km, the Michaelis constant, is how much substrate you need to add to get to 1/2 your maximum speed. So you just need to add more of it, therefore the Michaelis constant increases. Here's the actual mechanism of competitive inhibition. And our competitive inhibitor only binds to the free enzyme. So E plus I will make this EI complex with our rate constant Ki. And if we try that at the substrate, no reaction will happen because it is inhibited. Here's a graph showing that information as well. As we have more inhibitor, or the alpha gets bigger, you can see your Km, which is shown by this Vmax divided by 2 line, is increasing. So no inhibitor, we have Km here. If alpha equals 2, our Km is now 2 Km. And if our alpha is 4, Km is now 4 Km. The way that we measure competitive inhibition, the alpha value, is through a double reciprocal plot again. And when we look at a double reciprocal plot, we'll see with inhibitors, if it's competitive, they should all cross at the y-intercept because Vmax doesn't change. But your Km value is getting closer to 0 as you are increasing your strength of inhibitor, or increasing the amount of free inhibitor that you have. So this line we Burke plot crossing at the y-intercept is classic competitive inhibition. Uncompetitive inhibition will bind somewhere other than the active site, but it will distort the active site so your substrate cannot bind or cannot complete its reaction normally. Here we have Ki prime. The prime is for competitive inhibition, or uncompetitive rather. And you can see for uncompetitive, our Ki prime is a little bit different, where we have enzyme substrate complex, the free concentration of it, multiplied by the free concentration of inhibitor, divided by enzyme substrate inhibitor complex. And that's because uncompetitive inhibitor will bind to the enzyme substrate complex. So it will only bind when there's substrate already there. And then once it binds, it will distort the active site so the reaction cannot continue forward. So you'll get ESI goes to no reaction. If we look at the Lineweaver-Burke plot, you can see that uncompetitive inhibition, you get parallel lines. So that is classic uncompetitive inhibition. Why we get this parallel lines is that in uncompetitive inhibition, both Vmax and Km are decreasing. And you can't reverse this by adding more substrate because it takes out enzyme substrate complex. So if you are looking at a Lineweaver-Burke, you get parallel lines, that's uncompetitive. And our last type of inhibition is called mixed, which can affect both substrate binding, like in competitive, and catalytic activity, like uncompetitive. And basically, mixed is a mix of both types of inhibition that we talked about previously. It can bind to the free enzyme, and it can also bind to the enzyme substrate complex. So it has a Ki and a Ki prime as well. It has both types of inhibition. That's why it's called mixed or non-competitive. If we look at the Lineweaver-Burke plot for this, what you'll see is that the lines will cross not on the intercept usually. And that's because both Km and Vmax can change. Vmax will always decrease, so your maximum velocity is always going slower. Your Km can increase, decrease, or it could stay the same. So it is possible for all the lines to have the same x-intercept and different Vmaxes. That's also a situation of mixed enzyme inhibition. So what do we need to know for this? We need to know how Km and Vmax are changing with the inhibitors. We need to know how Lineweaver-Burke plot looks for these inhibitors. And we need to know how to calculate alpha, Ki, Ki prime, and alpha prime. So let's take a look at some of these questions. So I have an enzyme catalyzed reaction, and I add 5 nanomolar of a reversible inhibitor. My Vmax is 80% of the value it was without inhibitor, and Km's unchanged. So what type of inhibition is this? Well, this is mixed, because Vmax is decreasing, but Km's not changing. So if Vmax is decreasing, we only have a choice of 2, uncompetitive and mixed. But in uncompetitive, the Km also decreases. We aren't seeing that, so it has to be mixed. All right, B, what proportion of this enzyme have bound inhibitor? Well, that's 20%. That's because we're going 80% our maximum speed. So let's think about this logically. I have 100 enzymes. And let's say I have enough substrate so all 100 of these enzymes are bound. If I don't have an inhibitor, I'm working at 100% efficiency. Alright, let's say I add inhibitor. This inhibitor binds to 20% of my enzymes. That means the number of enzymes that are not bound by an inhibitor are 80. So 100 minus 20 equals 80. That means I'm going 80% my maximum speed, which is seen in the problem. That's why 20% are bound. C, calculate the inhibitor constant. Alright, so we are affecting Vmax, so we need to use the equation for Vmax apparent. Vmax apparent equals Vmax divided by alpha prime. Or alpha prime equals Vmax divided by Vmax apparent. Using my example of 100 enzymes, we can say my Vmax is 100. And if 20% are bound, that means my Vmax apparent is 80. It actually doesn't matter what numbers you choose here, as long as the ratio is always 100 to 80. So you could use 1 in 0.8. You could use 1,000 and 800. As long as the ratio is the same, it doesn't matter. And what we find from this is that alpha prime equals 1.25. However, I don't want alpha prime ultimately. I want the inhibition constant. That's Ki prime. So alpha prime equals 1 plus I divided by Ki prime, right down here. So 1.25, that's my alpha prime, equals 1 plus 5, because 5 is the amount of inhibitor I have, divided by Ki. Solve for Ki, and you'll see Ki prime is 20 nanomolar. That is your inhibition constant. Question 3, we have a Lineweaver-Burke plot here. A is our enzyme, and B, C, D, E, and F are all different types of inhibitors that are trying to inhibit the line A. So, which one of these is a competitive inhibitor? So a competitive inhibitor must cross at the same y-intercept as our substrate, which is A. So we either have E or B. Well, here Km has to increase, which means it's getting closer to 0 because we're in reciprocal plots. That means everything's kind of like the opposite. So if you're going closer to 0, that means you're getting bigger. Therefore, our competitive inhibitor is E. Non-competitive inhibitor. Vmax has decreased. So that means it has to be above our y-intercept for our substrate. So we either have D or F. So for this, that means Km has increased, decreased, or stayed the same, and the lines have to cross at some point. So our inhibitor has to cross the line with A at some point. The only one that does that is F. D doesn't cross the line with A, so F is our non-competitive inhibitor. Lastly, uncompetitive. You're looking for parallel line with A, and Vmax also has to decrease. So that means it has to be above our A line again. And we only have one line that meets both of those criteria. D has a lower Km and it's parallel to A. So our uncompetitive inhibitor is D. Question 4, we have a bunch of data on the table here, and we are trying to figure out constants from this. Now, the only way to solve this is to actually make a Lineweaver-Burke. So if you're watching this video and you had no idea how to solve this, pause it, close it, make a Lineweaver-Burke plot from this data, then try to solve it. All right, so our first question, A, what is the apparent Km and Vmax values in the presence and absence of this inhibitor? So if you did a Lineweaver-Burke, you should find out the inhibitor Km is roughly 25, Vmax is 100. No inhibitor Km is 7, Vmax is 125. What type of inhibitor is therosphingosine then? Well, let's take a look. Our Km has increased and our Vmax has decreased. So it could be competitive. And the reason I say that is that in real life data, it doesn't always match the theory. In that, sure, for competitive, our Vmax shouldn't change. And it doesn't change all that much. So based on real world data, this could be competitive, where we are just seeing some fluctuation in the Vmax numbers. Or it could be mixed as well, because we are seeing a lowering of the Vmax and a change of Km, which does fit our model of being uncompetitive as well. So either one of those is an acceptable answer. And with that, that ends our last problem set. Good luck on the final.